So unfortunately I pressed record on this lecture and started writing, but I had no memory key, and so unfortunately it's gone. So I'll have to carefully go through this, but we won't be able to write live. Now it's only just this page, and the good news is that this isn't really quite examinable, but it's good stuff for you to try and understand. There's some interesting stuff in here. Okay, so in the previous lecture we were talking about subsets as basically a subset of a set is you go through all the elements of the set and you kind of ask the question, is it in there or is it not in there? And these are yes no questions, and by answering them you come up with subsets. So for example, here we had S was the set containing X, Y, Z, and suppose you're asking an OR as a subset. Maybe let's write this here. That is not the real numbers. Or as a subset. So suppose you come up with the answers yes, no, yes. So that'd be the subset containing X and Z, just like that. Now another way of kind of recording this as such is to record your yeses as ones and your no's as zeros. And so this is something that you'll see probably in other computing modules, where 1 indicates an element is an element of the set and 0 indicates that it's not, kind of 1 being yes and 0 being no. This will be truth tables. So what you can do here is you can make a connection between subsets of an ordered set. Now we need an order on the set, which isn't always so easy, but I think any set you'll consider will have an order. So basically what you do is when you talk about a subset, you can say, okay, let's record the answer to the question. Is A in it? Yes, no. B in it? Yes, no. C in it? Yes, no. D in it? Yes, no. And when I say yes, no, I mean 1, 0, 1, 0, 1, 0, 1, 0. So for example, the subset A of S containing B and D would be no to A, yes to B, no to C, yes to D. No, yes, no, yes. 0, 1, 0, 1. So we see that this subset corresponds to this binary string. And similarly, if you take a binary string, for example, this one, and say, okay, say these are the answers to the question, is the first thing in the set, this is where you need the order, is the second thing there, is the third thing there, is the fourth thing there. And here you get no, yes, no, yes. No, yes, B is there. No, yes, D is there, B and D. So you got what's called a bijection, we're going to learn about later, between a matching, you can think of this for now, between binary strings of length, say 4, and subsets of a set with 4 elements. Okay, so you can see there's just as many binary strings of length n as there are subsets of a set of size n. And the question is how many? Now, we've written it up here, but maybe we should convince you of this using the binary strings. So probably the easiest way to do it is, okay, start with length 1 binary strings. So a binary string is just, string just means kind of a couple of letters together, and we're going to use binary strings, so the letters are either 0 or 1. Okay, so the length 1 ones, there's 2 of them, 0 and 1. Now what you can do is you can add a 0 and a 1 onto that, and a 0 or a 1 onto that. So what happens then is, for each of the length, say 1, if you can put on a 0 or 1, so there's going to be two length 2 binary strings from this, 2 length 2 binary strings from this, so the number of binary strings is going to double. And similar story, here's all the length 2 ones, and you can you can add a 0 or 1 onto that, 0 or 1 onto that, 0 or 1 onto that, 0 or 1 onto that. There was 4, you can put a 0 or 1 onto each of them, there will then be 8, you can multiply by 2. And you can keep going in this fashion, and you can argue kind of easily enough that the number of length n binary strings is 2 to the power of n, which is exactly the number of, if the set has n elements, that is the number of subsets. Okay, so we're going to do here's a kind of just an interesting example. Now this is more serious mathematics, it's not examinable, this bit, but it's just something cool. Right. So what I want you to think about is the closed interval 0, 1. Now what the closed means is that 0 is in there, 1 is in there, and all the possible numbers in between. Now what I'm going to tell you, and you need to take my word for it, because I can't quite argue this, is that every single number between 0 and 1 can be written as an infinite binary number. Now it can be done in the same fashion as you can write every number between 0 and 1 as a decimal. So that's using base 10. So say 0.72 is 7 tenths and 2 hundredths. And the relationship between these here is that 100 is 10 squared. The next number, say if it was 3, would be 3 over 10 to the power of 3. 3 over 10 by 10 by 10, 3 over 1,000. The third part being the thousandths. So, okay, so here's just some examples of numbers. So a half in binary is 01000 because just 1 over a half. This number here, 0.11 and then zeros, is 1 over a half and 1 over 2 squared. That's 1 over a half plus 1 over a quarter, which is 3/4. And you can show that, say 1/7, for example, is equal to this in binary. And then and that one, the pattern continues. Anything where the pattern continues can be written as a fraction, whereas with this thing, it cannot be written as a fraction. Remember, a fraction is a whole number divided by a whole number. And what we're going to show here is that for every subset of the natural numbers, you have a infinite binary string, and every infinite binary string, you have a subset of the natural numbers. Just kind of doing it in the same way as above. So imagine the numbers that you're thinking about taking a subset of. There's the natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 going on forever and ever. Take a binary number and say that these are the answers to, is this in my subset? So for example, here is 1 there, yes. 2, no. 3, yes. 4, yes. 5, no. 6, yes. 7, no. 8, yes. 9, no. 10, no. And keep on going. You will produce a subset of the natural numbers. Similar story, if you have a subset of the natural numbers, what you can do is you can form an infinite binary string. So this one, the answer to the questions 1 and 2, is it in the subset, or no? So you start with 2 zeros. Then there's 3 numbers, 3, 4, 5, yes, 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 1, 1, 1. Then 6 to 9 are all no's, they're all zeros. 10 is a yes, is a 1. 11 to 16 are all no, 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 so they're zeros. 17 is a yes, and then you just keep on going with zeros. So this kind of shows that every subset of the natural numbers gives you an infinite binary string, which can be, just put a point there, it's a number between 0 and 1. And each number between 0 and 1 gives you an infinite binary string, which defines a subset of the natural numbers. So what that means is there's a matching between numbers between 0 and 1 and subsets of the natural number. It's actually called a bijection. We'll learn about that later on. So we've got this weird stuff below that the number of subsets of the natural numbers, so this is subsets of natural numbers, number of them. Now number here, there's infinitely many. So this is why we use the word cardinality, or things are a bit more complicated. We say sets of the same cardinality if there's what's called a bijection between them. Okay, we'll learn later what a bijection is, but we won't worry so much about this cardinality business. But the number of subsets of natural numbers is kind of equal to, and I say number, or the size, let's just say number, it's the same as the number of numbers between 0 and 1. You can show that there's just as many numbers between 0 and 1 as there are real numbers. That's very complicated, I won't get into it. We've set up a bijection, and you can also show that there's strictly more subsets of the natural numbers than there are natural numbers. But that's, if you're doing a pure maths course, this is the kind of thing you'll be studying. For us, it's just something of a little bit of interest. Okay, now we're back to more what we'll be looking at. Okay, so given two sets x and y, we can form a new set called their union. Now you might be thinking of this thing as and you really need to break out of that. It's not like and, it's like or. This set, the union, is comprised of all the elements that are in x or in y. You don't want to think about and, because there's a different thing that's and. It's non-exclusive, so if something is in both x and y, which is a different thing to this, then it is also in the union. So it's all the things that are in x or in y or in both, if you want to say. That's I'm using the exclusive or there. So it's a mathematical or which includes elements that belong to both x and y. So for example, C is the counties in Ireland beginning with the letter C, and W is the counties containing the letter W, the union of them. Now, I really don't want you to use the word and, but we can kind of how would I build this set? What I would do is I would first, if I'm writing down C union W, so that's all the elements that are in C or in W, I write all the elements of C first. Then I write down any elements of W that I haven't already got. Now, Carlo, I've already written down. I don't write it down a second time. Okay, so this is what I mean. It's not C and W. It's like the only thing that's in C and in W is Carlo. It's C or W. So it doesn't matter that Carlo is an element of C and of W. It is still an element C or W. So in terms of a Venn diagram, now here the universal ambient set is probably counties, but we don't really have to specify that. Set C, set W. So let's say this together. Well, I'll say it in here. So C union W is composed of all the elements that are in C or in W, including the things that are in C and W, which isn't here. So it's non-exclusive. So it's not just in one of C or W. It's, now I'm going to use OR in the traditional sense, the exclusive OR. So it's all the elements that are in C or in W or in C and W. Okay. The intersection of X and Y is your AND. Okay, so this, the union is your OR, the intersection is your AND. It's the set whose elements belong to both X and Y. Okay. For example, for the sets C and W above, the intersection is just Carlo. Carlo is the only set, the only county that begins with C and contains letter W. In terms of a Venn diagram, now I've done it with C and W. I should probably do it with X and Y because these are supposed to be more general. And you kind of see they intersect, they kind of interlink, but I'm mad on that language myself. So let's say this is X, this is Y. Maybe we'll just write up here. So this is C union W, C or W, and here we'll do X intersection Y, X and Y. So this is an X and it's in Y. Okay. The relative complement or difference of sets. So it's set A without B. A minus B is also used, but usually A without B. I don't actually think we use this thing so much. A without B. So this is all the elements that are in A and not B. So I think we're just going to do a Venn diagram here. It's funny, I'm mixing between the letters, but it doesn't really matter. The only thing that really has to be consistent here is we call the ambient set U. So let's say set A, set B. So the set A without B is all these things. Actually, yeah, you might need these later on. Yeah. So this is the set, everything that's in A and B. Now in a second we're going to talk about the language of not, and this is going to be the same as A and not B. Okay. So for example, where C is the set of those born in Cork, and M is the set of those born in Munster, M without C consists of all those born in Munster but not Cork. So basically the other counties, whatever they may be, Kerry, Tipperary, Waterford, Clare, Limerick. What about C without Munster? Now that's probably not possible. So that's the set of people born in Cork but not born in Munster. Well, that's impossible, because if you're born in Cork, automatically you're born in Munster. So this thing is actually equal to the empty set. Now this isn't a set here, this is just saying, oh, the people born here. So there's probably something we can say here. It's that if say A is a subset of B, then A without B is equal to the empty set. So A being a subset, now it can be the same, it could be B, but it's everything in A is also in B. So this is everything in A and not in B but that's not possible because everything in A is in B. So you maybe pause this and try and understand this this thing. So this says everything that's in A is also in B. And this gives you everything that's in A and not in B. But that's not possible because, so I won't write any more here because I know it's a little bit confusing, but you should be able to understand this. Okay, in the presence of an appropriate ambient set, we can talk about the complement or the not. So we got the big ones are and, or, and not of a set A. Now we're going to write it as with a bar here, and it's going to be said not A. You can see it as A dashed or A complement. So we'll draw a picture of it here. And then we can go back to a question on a previous page. So if we have a set A here, not A is everything that is not in A. You could define it as U without A. You probably have to, because you can't just say not A. I mean, if you take A to be the set of students in this class, like there's loads of things that are not in it. I mean, laptop, lamp, memory disk, Coca-Cola. No, you need it to be in an appropriate ambient set. Otherwise, you can't really. It's just too many things. So really, it's all the things in the ambient set, but not in A. So this set here is not A. Okay. So for example, P is a set of prime numbers, and U is the natural numbers is assumed. So that's the natural place. Excuse the pun. That's the place where prime numbers live. Then not P is a set of natural numbers without the primes consist of natural numbers that are not prime. So for example, 1, 4, 6, 7, 8, 9, 10, 12, 13, 14, 15, etc. Because otherwise, like, loads of things are not a prime number. Do I put myself in there? Do I put my dog? Do I put my laptop? Do I put cereal bars? No. You need a proper ambient set. Okay. Combining these various ideas together gives us set algebra. And we'll actually do a question on that. So we're going to go back to page 13 and we're going to do this question here, which I kind of skipped over. Right. So just a little question. It's just testing, do you understand the symbols? Really understanding the symbols is kind of quite important here. Right. So write down not B. So as I just said, you don't like, got a can of Coke in the fridge. That's not in B, but it doesn't go in the set not B. It's all the things that are, we'll just write it down here. It's the universal ambient set without B. So, okay. So basically the way you want to do this probably is take set 1 to 8 and just don't put it in if it's in here. So 1 is fine. 2 is fine. 3, no, that's in B, so it doesn't go in not B. 4, no, it's in B, so it's not in not B. 5, no, it's in B, so it doesn't go in not B. 6, no. 7, yeah, that's fine. 8. So there's probably 2 things we could write down here. So maybe for some people, it will be easier to think of the subtraction. So that not B is everything in this, take away everything in this. So it's like take this set and take away the 3, 4, 5, 6. That might be the way you think of it. Something that kind of is a bit kind of came to the fore there is if you think about the things that are not in not B, now maybe it's this clear. So this is a double complement. This must be B. If you're not in not B, you're in B. And that works the other way around. B is not B. So if it's not in B, it's not in B. Actually, I'll write that one down. It's a bit confusing. If it's not in B, then in not B. So 1 is not in B, so it's in not B. 2 is not in B, so it's in not B. 7 is not in B, so it's in not B, this kind of crap. Okay. And next thing. Now, there's a temptation here to kind of write down the answer, but really you should just build this up slowly. Okay? Now, we've already found not B, so let's build up slowly. Let's next find not C. So C is 4, 5, 6, 7, 8. So what's not in C is 1, 2, 3. Okay, and now we'll build it up. We'll find the intersection. So what's in not B and in not C? So I see 1 is in not B and not C. 2 is in not B and not C. And there's no more numbers. So this set here is equal to 1, 2. And then it wants us to find A union this. So that's all the elements that are in this or in this. And my recommendation here is if you're doing a union, write down everything in the first set. So I need to write A union, not B, intersection, not C. And this is equal to, so write down everything in A, 1 to 5. So that captures everything in A. It'll also capture everything that's in A and B. And then all you have to do is capture things that are in B but not in A. And if you look at, sorry, in this set but not in this set, but actually if you look at it, 1 and 2 are already there, so you're done. Okay. So that's that. Next question, find or otherwise write down this. So this, you can do a similar story. You can find B or C, then find not B or C, and then find a union. But what we're going to learn a bit later on, and it's not here, is that not B or C is equal to not B and not C. We'll learn about it a little bit later on. It's called one of De Morgan's laws. Okay. Right, so we've been talking about, this set algebra. And so a key feature of set algebra and linked to logic are set identities. So these are formulas where you've got formulas in some sets using unions, intersections, and knots, and saying that two things are equal to it. Now I can write down something like, so formally, maybe for example, so some formula, first formula A, B, C, now I'll just do one, for example, equal to some other formula containing A, B, and C. So just two formulas, and the point is it doesn't matter what set you actually put in for A, B, or C, they'll always be true. So a similar story with algebra, no matter what numbers you use, say if it's an equation or what's called an identity, it'll always be true. So let me just give you an example of an algebra one. So an algebra one would be like x plus 1 squared is equal to x squared plus 2x plus 1, and that's true no matter what number x you put in. You'll get these two things are the same. So this is the same no matter what three sets you use. Well, let's just do an example here. So not A or B is not A and not B. No matter what set you put in here, these two sets are going to be the same. Okay. So set identities combine a number of variable sets. So the variable sets would be the A and B, and various operations, union, intersection, not, and sometimes relative complement, and are true for all possible variable sets. So this is what we just said. Now, one of the things you might be asked to do is show the two sets are equal. So actually there's a third thing that we're going to use in this module. So set identities are actually a little bit different here, but you can use laws of sets, which we'll get to a bit later on. Okay. So actually these questions are not quite of this type. So this first thing here is, this is too hard, okay? So it's to show two sets are a subset of each other. So if A is a subset of B and B is a subset of A, the only way that can happen is if they're the same set. There's just an issue here, is that this is kind of different to this, and this laws of sets is referring to this. and this is kind of in both of them. Alternatively, you can show that they have the same truth table, but we'll see that a bit later. To show the two sets are not equal, you need to find an example. Well, you need to find, okay, so if it is a specific example of a set, you want to find two sets, are they equal? Find an element. So actually this is just, there's a bit of confusion here, and I'm just going to spell it out, right? I've got these set identities, which are true for all sets, and here is kind of talking about specific sets, are they equal? So these are equal no matter what A and B are, but there could be different things where I'm actually talking about specific A and Bs. So maybe what we should do is just finish up here and say that if you want to show the two sets are not equal, usually what you'll want to do is find an element that is in one set but not the other. And if it's a set identity that you want to say is false, usually you want to come up with an example of a situation where the identity is not actually true.